Hey everyone, let's get straight to the exam 2 practice problems explanation video. Question 1. Male donkeys and female horses can mate to create meals. Offspring of meals have never been observed. True or false? By the biological species concept, the BSC, meals are not species. That is true. The BSC demands that offspring created are able to create offspring themselves, and meals are infertile, so meals are not species by the BSC. Question 2. True or false? Dinosaur fossils can be categorized into species using the BSC. That is false. The BSC asks for interbreeding between the organisms, but fossils are bones, and there's no way to see whether the creatures that ultimately became those bones ever interbred with one another. So, almost every scientist would say, oh yeah, but, they're still species, but you would just have to identify them using a different method, like analyzing the bone structure. Question 3. Triangle snails reproduce clonally. One snail goes to two identical snails. True or false? Triangle snails are a species by the BSC. That is false. The BSC calls for interbreeding, not just breeding in general. So interbreeding, between two separate entities. So snail is self-involved. It only breeds with itself. It only involves itself. You would have had to have that snail breed with another snail for it to be considered a species by the BSC. Question 4. Timmy's biological parents had sex in the room, while Timmy waited in the motel hot tub for hours. Timmy is now infertile. By the biological species concept, is Timmy human? This is a ridiculous question, but by the BSC, he would not be human. He would be not human. That's because while he probably could breed with someone, it would not produce any offspring. There are a lot of downsides to the BSC. Question 5. Matchamps and shuckles are often observed mating with each other. Such matchamps always experience miscarriages in the second trimester. Are matchamps and shuckles the same species? If not, is an isolating factor pre or post-zygotic? So they're mating with one another, and they're separate things that are interbreeding, but they don't actually produce any offspring. The miscarriages happen before that. So there's some kind of isolating factor in play. But nope. No. The zygote is formed. So the shuckle's sperm, uh, that's weird. Will interact with the matchamp's egg, and they made that zygote. And that zygote was carried at least through the first trimester, but then was miscarried as the matchamp's body saw that it would not be that it is not able to be a viable offspring. So while the zygote was created, it was gotten rid of. So that would be post-zygotic. Post meaning after the zygote was made, where the zygote is the fertilized egg. Question 6. GPs and troglodytes appear identical but do not interbreed. Are they the same species? If not, is the isolating factor pre or post-zygotic? So they don't interbreed. So by the biological species concept, they are not the same species. But is isolating factor pre or post-zygotic? So they never bred in the first place. If they don't breed, that means the sperm doesn't have any chance to meet the egg and at least temporarily become a zygote. So this isolating factor would have to be pre-zygotic. The zygote was never formed. It's before the zygote. Question 7. You like to keep pet beetles and other critters. You keep one male ladybug in a Tic-Tac box and one female ladybug in a 0.9 pencil lead box. You don't keep them together because you don't have enough available containers to imprison their potential progeny. The Altoid tin is currently being used to house your pet tortoise. Are the two ladybugs separate species? No. So just use this is just a little bit of logic, but just because they are separated, that doesn't mean that they wouldn't breed. Question 8. Species Angelina and Jolie have long been considered different species. Organisms of Angelina have been seen mating with those of Jolie and producing offspring cleverly coined Joe-Angelina-lees. Joe-Angelina-lees have been observed mating with each other and increasing in number without any Angelinas or Jolies present. True or false? By the BSC, Angelina and Jolie are the same species. That is true. So Angelina and Jolie are interbreeding and they are producing offspring. And those offspring are producing offspring of their own, so they're viable. So all the tenets of the BSC have been satisfied. Question 9. Fundamental niches involved abiotic factors, while that would be non-living factors. While realized niches involve both abiotic and biotic factors, which would be living stuff. True or false? It is impossible for the realized niche to be greater than the fundamental niche. That's true. So the fundamental niche are all the possible ranges that an organism could theoretically survive in, and that's the max. That's all the theory that they could be in. But the realized niche could only potentially be equal to it at the very most. So that's no. Question 11. True or false? The realized niche is usually the same as the fundamental niche. That is false. The realized niche is usually much smaller than the fundamental niche because there are other biotic factors. So there's like, there's organisms like that compete with it, use up resources, there's predation, whatnot. Okay, question 12 and question 13 use the following graphic. Question 12. Ranges A, X, and Z. Identify the barnacle species each range is for, Jalamus or Semigallus, and what kind of niche the range represents. Fundamental, realized, or not enough info given. Okay, so A, you see that corresponds with Jalamus. We'll just put a C. And well, let's look over here. This is another range for Jalamus, and it seems to be much smaller. So this one is likely the fundamental niche before it is limited by other organisms. And X is much smaller than this one. It would be the realized one. And we see that with the presence of another barnacle, it does much worse. It is limited. So Z, Semigallus. Now it could be we don't have enough information to determine what kind of niche it is. It could be the fundamental niche or it could be the realized niche. So the fundamental niche might actually go all the way up here. It might be able to survive all the way at this range, but the Shalom is limited. Or it might only be able to survive up to this range, and these just happen to be able to exist around that area. So we don't have enough info. So question 13 gives us that info, or at least to assume some of that info, which is that the fundamental niche for Semigallus is the same range indicated by A. So yeah, it would go all the way to the top. Which barnacle is a better competitor? So while the Semigallus is not able to occupy its full fundamental niche, they share the same fundamental niche, and the Semigallus is able to occupy a much larger area on this slope. So Semigallus would be the better competitor. Question 14. Thermus aquatus is a bacteria found within hot springs, which can reach temperatures as high as 170 degrees Fahrenheit. Its DNA polymerase protein, coined Taq polymerase, is one of the most important tools in modern science. It enables efficient PCR. How might the structure of Taq polymerase compare to that, of human polymerase in terms of rigidity? Okay, so this is kind of a peculiar question, but you'll probably get tested on it on the exam. So proteins need to bind to their substrate in order to function properly. So when it's really cold, things tend to slow down, and the proteins get very rigid. They don't move around a lot, and that inflexibility means that if it's too cold, they cannot bind to their substrate and they can't function. But if it gets too tight, then your protein will just continue to vibrate and move around, and then it will start to denature as the age bonds are broken within it. So, yeah, an organism that is in a very high temperature environment, like uh, the, the bacteria attack, um, needs to be able, its proteins need to be able to withstand a very high temperature. That means that they should have a lot of connections between them. They should have very strong intermolecular forces, so they should be very rigid. And humans do not live in anywhere near as hot of a temperature, so we can expect our attack polymerase to be much more rigid in order to withstand the very high temperatures. When exposed to poor water conditions or arid environments, axolotls, which are usually perpetually in their juvenile state, can occasionally morph into their adult terrestrial forms. Is this an example of acclimation? How about phenotypic plasticity? Into both of those, that would be yes. So acclimation would be an organism changing in response to its environment. So there was less moisture, and then it changed. So that's acclimation. Phenotypic plasticity. Let's say that you had 100 axolotls, and they have about the same genotype. And then you take half of them and you expose them to a dry environment, and some of those will morph into the terrestrial form. They have the same genotype, but from that same genotype, multiple phenotypes were developed. So that was plastic. Global temperatures are expected to be about 2 degrees higher by 2050. A species with a narrow versus broad thermal niche will likely be less impacted, while a species with a narrow, broad thermal niche will likely do worse. So global temperatures are increasing. And the first statement looks for something what will make them less impacted, like more resistant to the change. And that would be something with a broad thermal niche. Because if you have a narrow thermal niche, that means that if you go outside of it, you will not do well. And if it's narrow, 2 degrees could easily set you off course. But if you have a broad thermal niche, you might just operate at a different temperature. So that's what we said. While a species with a narrow thermal niche will likely do worse. Again, if it has a narrow thermal niche, that means that even slight changes could put it outside of its niche, and then it will not be able to function. Question 17. The population of butterflies have individuals who are red, blue, and brown. Each phenotype incurs advantages. Red butterflies blended with the roses in the area. Blue butterflies blended with the blue poppies. And brown butterflies blended with the surrounding bark. Is this an example of acclimation? How about phenotypic plasticity? Evolution by natural selection? So acclimation is no. And phenotypic plasticity is no. So both acclimation and phenotypic plasticity involve an individual and changes within its own lifetime. So based on the information at hand, it just seems like they're born blue, they're born brown, they're born red. It isn't response to the environment, they don't change, they're just kind of that way. But this would, yes, likely be, these characteristics would likely be due to evolution by natural selection. So we can infer natural selection because there are advantages that these traits have within their environment that likely allowed them to survive and reproduce. And we're talking about evolution because in this population, it seems like they have blue, brown, and red. So because they all inferred advantages, those genotypes or those alleles were kept within that population. Question 18. Generally, what might be trade-offs of being well adapted to a very high temperature? A very low temperature? How about a broad range of temperatures? So let's look at a high temperature. So at a high temperature, you're able to function very well at high temperatures, but that means you're not able to function at low temperatures. Bad at low. And you're also more susceptible to fluctuations. Bad at fluctuations. And then you just basically reverse this for low temperature. You're bad at high temperatures, and then you also aren't resistant to fluctuations because a change might put you outside of your zone. Okay, and then a broad range of temperatures. So you can function at a lot of different temperatures, so good with fluctuations. But when you're interacting with those like specialists, you're worse than specialists generally. at their given range. And oftentimes, generalists have to sacrifice not only fitness, but is energetically not the most favorable to be able to be good at so much or decent at so much. Question 19. There is a population of humans living in a house. Here's what happened in a month. Melinda gave birth to triplets. Angelina gave birth to non-fraternal twins. Huh. Then they would just be twins. I didn't realize that. Anyway, Francine gave birth to an illegitimate child. Raphael is sad but decides to work through the relationship through intensive marriage counseling. His greatest fear is that he might not be able to treat Rafi with unconditional love. Mauricio got kicked out for not paying rent. Brothers Liam and Bobby move in. Melinda died, and Dustin got hit by a car. Dustin's surgery did not go well, and then he died. Emmy, a long-term resident of the household, got back from their Spain trip. What was Delta N for this house over the month? So, this stupid, like, fifth grade sounding problem does actually have some merit. We're looking at what different things can impact a population size. So over here, looks like births can increase a population, deaths will decrease a population size, immigration will increase a population size, and emigration will decrease a population size. So we're looking at all those, and it looks like there's an equation given over here. So that would be, oopsie, that would be delta n is equal to births plus immigrants divided by deaths plus emigrants. So now we can look at our births. Triplets. So plus 3. And then we have twins. And we have a child. Cool. And now let's look at the immigrants. So, and immigrants would just like be people entering the population. So, looks like Liam and Bobby, that's 2 people. They entered. And then Emmy moved back in. So that's 1 person. Cool. So these are the increases. And now let's look at the depths. So Melinda died. That's 1. And then Dustin also died. And then let's look at the emigrants. So that's people who left the house or left the population. And it looks like only Mauricio. Maybe not willingly, but he did leave. Cool. So delta n is equal to 3 plus 2 is 5 plus 1 6. And then so that'd be 6 plus 3 minus 2 plus 1. So that would be 9 minus 3, which would be equal to 6. Our delta n is 6 people. So that is our change in our population over the course of that month. Okay, when a population's number completely plateau, what is growth rate R? So let's say that we're looking at this chart over here, right? And this is time, and this is population size. So it looks like this. And then I can't draw a straight line, but let's say that it's completely straight. That means our growth rate R is equal to 0. There is no growth happening. There is no, the population is not diminishing. Nothing's changing. Are birth rate and death rate equal? Maybe, not necessarily. Because remember, there are other things that can impact the population size as well. There is, for increasing it, there would be immigration. And then for decreasing it, there would be emigration. So what might happen is, let's say that there are more births and deaths, right? Which would suggest that your population is increasing. But let's say that you have a ton of immigrants. Like a lot of things are leaving the area. So that would result in a negative growth rate. So as long as there's a balance of increasing forces and an equal amount of leaving forces, then our growth rate would be R. A population grows at an exponential rate and eventually grows at a logarithmic rate. So this is very common in populations. They initially grow very quickly, very large because of the availability of resources, but as they reach their carrying capacity, the it goes slower at a logarithmic rate. During which stage was population growth more drastic? Oh, we just talked about that, but that'd be exponential. During which stage was R greater? That would be exponential. Your growth rate is greater at the exponential one. During which stage is R constant? That's exponential. So that's more definitional. But what variable is population size approaching? That would be K for carrying capacity. So as you enter logarithmic growth and you approach that K, your growth rate is steadily going down. It's not staying constant like the exponential stage. So R will be decreasing with the logarithmic growth. And why might the population have shifted from exponential logarithmic growth? That's just less resources. You are approaching that carrying capacity. Okay, we're getting into word problems now. Question 22. A population of long-tailed grass lizards currently has 1,200 members. Their annual per capita birth rate is 0.14, and their annual per capita death rate is 0.08. What will be the delta n? So that would be the change in the population size of the population over the course of 4 years. What will be the population size in 4 years? Round down to the nearest whole lizard. So, okay, so we want a final population size, but they did not mention anything about carrying capacity. So that means that we're just looking at this equation. Cool. But we are not given R. We're given the birth rate and the death rate, but we need our growth rate. And looking over here, our R is equal to our birth rate plus immigration rate minus our death rate slash our emigration rate. So let's write that out. So that would be our BR plus IR minus DR plus ER. But we are not given any information on immigration or emigration. And in that case, we just disregard them. We just mark them as 0. So we only worry about the birth rate and death rate. So that would just be 0.14 minus 0.08. So our R is 0.06. Cool. So now we have that, we can just plug that in. So, but let's label our variables first. We want it after 4 years, so this would be the n after 4 years. And then the initial population, let's call that ni for simplicity, times 1. Well, we already know our r, but we'll just put r here for now, and we'll put it in later. And then our delta t. So our delta t would just be 4. This happened over the course of 4 years. So let's plug some stuff in. N4 is equal to Ni, our initial population. So that's 1,200, 1.2k. Okay, we already know that would be plus the growth rate, so that'd be 1.064. And now we're done. We just need to plug some stuff in and then do a couple other stuff. So that would be 1.06 to the 4th power. And then we multiply that by 1.2k. Cool. So our population after 4 years is 1514.97. But we round down to the nearest whole lizard, so that would be 1514. Cool. So now we know our population after 4 years, but the question also asks for what was the population change. And that's very easy to calculate. We know our population at the start was 1,200. So that would just be 1514 minus 1.2k, and that would just be a difference of 314. So delta n, the change in the population over those 4 years, so we can put a little 4 up here if you want, was 314 lizards. Cool. Okay, this one is kind of wonky. I'm not really sure why, but I will explain why it's wonky. So in 2018, Monaco had a population of 38,682. In 2020, Monaco had a population of 39,244. If growth rate is constant, what will be Monaco's population in 2140? Round down to the nearest whole person. So we're looking for an end population or a population after a given amount of time. But we're not given carrying capacity. That doesn't mention any of that. So that means that we're looking at this equation. So that would be n. In fact, we'll even mark it. So n at 140 is equal to our n0 times 1 plus r over delta t. Okay, so we are not given r, but we can calculate it. And we calculate it using this equation over here. But I have an expanded version that I think is a little bit easier to use. So we're going to use that. So let's write it out. R is equal to your population size at a later point minus your population at an earlier point divided by your time at a later point minus your time at an earlier point. And all this is divided by your population at an earlier point, but for math reasons, we're going to represent it like this. Times 1 and earlier. Cool. So let's plug some stuff in. So R is what is our population at a later point? Our later point will be at 2020. So that would be 39,244. Our population at an earlier point that would be 2018. That would be 38,682. Then our time at a later point was 2020. Our time at the earlier point was 2018. And then our population at an earlier point, we keep it consistent, was 38,682. So now we're just going to plug some stuff in. We'll do the stuff in the center first. So that would be 39,244 minus 38,682. Cool. And then we divide that by 2020 minus 2018. Well, that's just 2, but we'll type it for fun. Cool. So that'd be 281. And now we divide that by the, oopsie, I don't know why I did that. And then we divide that by the earlier population size, 38,682. Okay. So our R is equal to 0.007264, whatever. And we want to use this equation over here now that we have obtained our R. So that would be equal to n to 140 is equal to n0. Okay, so for our n0, whenever you're doing a problem like this, you can choose any of the populations that you're given at a time as a starting point, as long as you keep stuff consistent. I'm going to talk about what's janky about the problem in a second, but for our purposes, we're going to choose the 2021. So that would be our n at 2020. So our n at 2020 is 39,244. And then our growth rate would be 1.0, because you add the 1 onto it. I don't know why it's doing that. 1.007264. And then our delta t would be our final time minus our initial time. So that would be, that would be our 2140. That's the year, the end time, minus 2020. Okay, let's do some math. Okay, here's a little trick you can do. So we're going to do this area first. We're going to add that to 1. You can use the store function to save something for later. So you hit the store button over here, and you hit alpha, and you can assign it to any letter. So we're going to assign it to F. And then we can bring up F later. So just like alpha f, there it is. So we're going to bring that to the 2140 minus 2020 power. Look at that, multiply that by the population at 2040, 2020, at 244. Cool. So we get 993,538. We round down to the nearest whole person, so there it is. That's our population in the year 2021-40 from Monaco. So here's why the problem is so janky. As I said, you should be able to use any starting point for the later equation, and it works out for the other questions that I made, but not for this one. But I don't want you to get too confused. But remember, so look, we used the 2020 data, but we should have also been able to use the 2018 data. If someone knows what happened, let me know. But if nobody tells me, I don't really care that much. So we use the same thing, but we use 2018 data. So we still have our thing saved in our F. So that would be F to the 2140 minus 2018 instead. And then we multiply that by the population of 2018, which would be 38682. And we see that we get a number that's 5 off. I don't know why this happens. They should be the same. And on the exam, they'll probably be written better, so you can use whatever you want if they don't specify. Okay, let's move on. Okay, this one is different. Jerry Garcia Vargas is growing a colony of bacteria sourced from his cell phone screen in a petri dish. He estimates that the carrying capacity, we're talking about carrying capacity here, of the environment, given the space in the food he provides, to be 100,000. Using counting methods, he estimates the population on day 2 to be 4,000. On day 3, 8,000. Of his measurements, what will be the population of the colony by day 4? Use the population from day 3 in this calculation, round down to the nearest whole bacterium. Okay, so we're talking about carrying capacity here, which means that we have to use this equation. It'll be on the test, and it's the only one they give you involving carrying capacity. So we have to use that one. So let's take a look at it. So that would be our n at the final time. So that would be, let's say that's day 4, is equal to our starting one plus our growth rate multiplied by our initial, if I'm going to use i's, I got to keep it like that. And that would be our carrying capacity minus our initial population size over our carrying capacity. Okay, so we're not given our r, but we have the ability to find it. And let's solve it over here. So that would be our r is equal to our population at a later point minus our population at an earlier point. And then that's divided by our time at a later point minus our time at an earlier point. And this is divided where we can multiply it by the inverse of our earlier population. Cool. So now we just substitute this stuff in. Our later time would be day 3. So that would be 8,000. And our earlier one would be day 2. So that had a population of 4,000. Cool. And then our later time was day 3. And then our earlier time was just day 2. Times 1 over our earlier time. So that would be our 4,000. Okay, so this math, we can do it by hand. So 3 minus 2 is 1. 8,000 minus 4,000 is 4,000. 4,000 divided by 1 is 4,000. 4,000 divided by itself, 4,000 would just be equal to 1. So all of this is just equal to 1. So our growth rate is 1. And now we're able to do some math. So our n day 4 is equal. So it said use the population from day 3 for our data. So they will specify this on the exam because you will get different results if you use the day 2 for your initial compared to the day 3. So, but they'll tell you. So we're using day 3, so that would be 8,000. Our growth rate is 1 times 8,000. And then that would be 100,000 minus 8,000. Over our carrying capacity, which is 100,000. Cool. So n day 4 is equal to 8,000. 1 times 8,000 is 8,000. Oops. Plus 8,000. And 100,000 minus 8,000 would be 92,000. And that's divided by 100,000. So, and day 4 is equal to 8,000 plus 8,000 times, okay, we just simplify it. That would just be 0.92. Okay, let's do some math. Have you ever in that, whenever you just have like a gap between them, that implies multiplication. So 0.92 times 8,000. Cool. And now we just add that on to 8,000. Rad. Okay, so our population at day 4 for this bacteria colony is 15,360 bacteria. Cool. One more to go. George Washington Carver has concerns of the field over the field mice running rampant in his peanut fields. He adopts 3 cats to assist with infestation. Using his power, he knows that from 1922, which had a population of 30,000, to 1924, 2,000 new mice were born. 1,800 mice were hunted by cats. 100 died to other causes. 500 mice left for neighboring farms, and 300 were catapulted in. Assuming that the population change, growth rate, remains constant, what will the mice farm population be in 1938? Round down to the nearest whole mouse. So they didn't mention carrying capacity, which means, and we're looking for an N population, which means that we're just looking at this guy over here. NT is equal to N initial times 1. And also, like whenever N0 and I, but they both mean initial. I should probably have just kept N0 to keep it consistent. Okay. And then to the delta T power. Okay. So we are not given R, but we have the ability to find it. So let's look at R. R is equal to delta N over delta T over N1. Okay, so we don't have the delta N at the moment, but we can find that. Oh, actually, oopsie. Let's use a better equation. No, actually, I like that equation. Darn. I'm sorry. So we want to find the delta N. And they give us all the information we need to find that. They give us the births, they give us the deaths, they give us the emigration, they give us the emigration. So our delta N, we look at our positive stuff, which would be births plus immigrants. And then we subtract our deaths plus our emigrants. Okay, so let's look at our births. And this is a period of 2 years over from 1922 to 1924. So our births are 2,000. Our immigrants, I guess those would be the mice that were catapulted in. And then our deaths, that would be 1,800 from cats, but 100 also died. But a death is a death, so that would be 19,000. I mean, sorry, that would be 1,900. And our emigrants, so 500 of the mice left. Cool. So that would be 2,000 300 minus 2,400. So we're actually looking at a negative population growth here. So over the course of 2 years, that population was diminished by 100 mice. Cool. So now we have our R. So our N, and we're looking at for 1938. Yeah, let's say our initial population, we'll use 1922. And this problem is janky like the other one, so you can use either 1922 or 1924. Oh, oopsies! I'm sorry. I'm so tired. Um, we didn't actually get the R yet. We only got the delta N, which is necessary to find our R. So let's find our R right now. That's my bad. I'm sorry. So our R is equal to our delta N. That's negative 100 over our change in time, our time period. So that's from 1922 to 1924, so that'd be 2. And then we multiply that by our initial population, or our earlier population. So in this case, that would be the population in 1922, which was, it was 30,000, I think. Yeah, 30,000. Okay, so 30,000. Oh, oops, it's actually divided. I'm sorry. So it's divided by 30,000. My bad. So that would be equal to negative 50 divided by 30,000. I'm sorry, guys. Yeah, okay, negative 50 divided by 30,000. Cool. So it looks like we have that. Cool. So we're gonna use our store function and save it under A. But our R is equal to negative 0.0016 repeating. Okay, so we have our R value now. So our initial population, and we're using 1922 as our initial one, would be 30,000. And then 1 plus R, so what was that? 1's dead. That would be 0.998, whatever. And then our delta T, so delta is final minus initial. So our final time was 1938 minus 1922. Cool. Okay, let's save this function underneath A. We'll replace it. Cool. Whatever. So I already did that. I forgot that. Whatever. So we'll bring it to the, you don't need to use parentheses, 1938 minus 1922. Okay. And then we multiply that by 30,000. Cool. So our population at 1938 was 29,209. We round down to the nearest whole mouse, so it would be like that. Okay, so just so I can show you that it works both ways. Yeah, we're gonna do it using the data from 1924 as well. So we have our A, which corresponds to this, but this time we bring it to the 1938 minus 1924 power. Cool. So we have that, and this time we multiply it by the population in 1924. Now the population of 1924, well, we know the delta N change. The delta N change was minus 100. So the delta N would be 30,000 minus 100. And we see that we get basically the same thing. Yeah, 29204. Well, now that I'm thinking about it, I think that my question was actually valid, but it's just that the numbers were greater, so there was more room for error. I don't know. Anyways, thanks for listening. Email me if you have any questions at all. I will email you back. And I like when students ask questions. I think it's fun. Well, thanks a bundle.